Okay, so good day everyone. So for today, our topic is about module number 5, that is networking 1. Okay, so in our interconnected world, network and system administrators have their hands full. No? Almost every type of organization these days relies on a network and computer system to do business, teach, engage in charity work, or serve its customers. No? And those systems are complex. No? They need constant updating and repair. And the people who set up and manage them have to be trained. No? That's where system administrators come in. But what makes an effective system administrator? No? How do you know if it's something you will excel at? No? So the right education and training can take you a long way in developing the competencies you'll need to be a successful. So let's take a look at 5 indispensable skills for any professional in computer networking and system administrations. No? Excuse. Number 1, of course, is the computer expertise. No? It never hurts to be a teach nerd. No? Or teach nerd. No? But if you're going into network and system administration, you will be learning into tech hard. No? The job includes installing network hardware and software, maintaining security, in managing servers, desktop, and mobile devices. Also, within your responsibilities, keeping workstation connected to the central network, no, ensuring that the different kinds of computer equipment work together seamlessly, no, navigating circuit boards, processor, chips, no, electronic equipment, and computer applications, no, and programming, no, so designing and administering wireless infrastructure in its supporting system. For starters, no, you must have a strong understanding of the design and installation of local and wide area networks, so yung LAN or WAN. But network administrations, no, involve so much more. You'll also need to understand meaty topics such as internet working, cloud computing, and how to manage virtual servers, and of course, computer security. Another is the people skills. No? Seems a little counterintuitive, right? No? But the best computer people are also people, no, the people, no. You won't be working alone. So a strong, healthy relationship with your bosses and coworkers is crucial. Depending on your field, you may also be interacting with customers or clients, no. Training team membership so they feel confident in the use of new hardware or software requires more than technical know-how. So you must be clear, communication or communicator and good listener at the same time, especially with people who don't have the depth of technical knowledge or know-how that you possesses. No, minsan kasi it's too hard for us to communicate with those persons who are not technically inclined. No, another is the ability to multitask. No, can you work on multiple problems at once? No, if not, systems and network administration might not be the field for you, because the challenges come fast and furious. No, organizations and prioritizations are the key, no, for this part. No, collecting data to evaluate a network's performance, you'll be doing that. Adding users and assignment security permissions, that too. Researching and recommending better approaches for the system task, it's on the list. Constantly upgrading your skills as the technical world transform at an ever quicker pace, you bet. No? Another is the technical or critical thinking skills. No? Meanwhile, if you enjoy fixing things, this line of work offers up a problem solver's paradise. No? You'll face the constant challenge of getting your system to work better and faster. And at the same time, you'll be putting out fires that will inevitably pop up, some predictable, others not. So administrator have to be proactive to stem problems before they reach disaster status. No? And the pros or the advantages, put plans in place at worst case scenario. So ask yourself, can you think through all possibilities and then land on the best solution? Do you involve others in your decisions, ensuring everyone is on the same page? Are you okay with shouldering blame and using any failures to improve the status quo? If so, complies with companies will want you on their IT team, no? Another is the communication skills. Actually, no, this will be a good practice to an IT practitioner to be a good in the communication skills, because as a system administrator, no, you'll be able to talk with different people, no, in an organizations, no? So communication skills is probably the catch or catch all attribute for most everything you'll be doing. Whether that's training others, working on solutions together, or documenting network configurations, talking through possible upgrades, making recommendations, and organizing data into a usable form. All the knowledge in the world won't matter if you can present all the information clearly in writing, in person, or in a big meetings, no? Because I think, no, during your defense, you are encouraged, no, to deliver or to demonstrate your system in a volume of people. Okay, and even during your application, there are certain company who are conducting a panel interview. So during that time, you have an idea, you have an edge, no, if you could able to practice this communication skills during your college days. Okay. Excuse. Now, maybe, no, all of you are familiar with the OSI stack, no? Since you already, I think, finished with operating system, or you have an ongoing operating system, no? Network stack are complex, as you can see here, no? And multi-layered, no? We have multi-layered, no? Systems that map applications layer data structure to bits transferred over physical media and back again, no? So the open system interconnection, yung OSI na tinatawag natin, no? Model is a conceptual framework, no, that provides a protocol agnostic description of how the various layers, no, of a network stack combine to enable network communication. The goal of the OSI model or OSI stack is to enable diverse communication systems, no, to better interoperate using standard communication protocols. The OSI model or stack takes a complex system and breaks it into several discrete layers based upon the various tasks fulfilled by network protocols. No? And this abstraction makes it easier to troubleshoot issues, identify security risks, and describe network layer attacks. No? As a theoretical model, the OSI is not necessary for modern networking protocols to operate. However, it does make it easier to identify security risk and analyze the capabilities of cybersecurity solutions, making it an invaluable tools for network security. We have here, no, the 7, no, layer. We have the application, presentation, session, transport, network link, and physical. And this will be discussed actually thoroughly in your operating system subject. But the OSI model is broken up into 7 layers as what we have here, right? So each layer fulfills an important role within a networking stack and communicates with other layers by exchanging protocol data units, yung PDU na tinatawag natin. So the layers in the OSI model are commonly referred to by name or numbered 1 to 7, from lowest level to the highest level. And they are, the number 1 is physical layer. Ito yung nasa lower level natin, ano? Medium in bitrate po yan. So, the physical layer is where the raw bit stream is physically transmitted over a physical medium. So, the layer 1 of the PDU or yung protocol data units, yung PDU, is the symbol. No? And this include translating bits to electricity, light, or radio signals, no, and controlling the rates at which they are sent over the chosen medium. Number 2 natin, of course, is the data link. No? The data link layer breaks data to be transmitted into frames for transmission at the physical layer. So, it also manages connections between 2 different nodes, including setting up the connection, identifying and correcting any bit errors that occur at the physical layer, and terminating the connection once the session is complete. Number 3 is the network. No? At the network layer, the focus actually expands from a point-to-point link to include many interconnected nodes within a network. So network layer device operate on packets and are responsible for routing traffic to its destination based on IP addresses. No? Number 4 is the transport. No, sorry. Okay, this is the transport, number 4. No, so that is most of the TCP. No, the transport layer is the first of 4 host layer with the rest referred to as media layers. So the transport layers PDU is the segment or datagram. Now this layer manages the transmission of data between nodes, including ensuring that data arrives in the correct sequence and that any errors are corrected. And the transmission control protocol operates at layer 4. So you are all familiar with transmission control protocol. Doon po siya nagra-run sa layer number 4, transport layer. Number 5, of course, is the session layer. No? The session layer manages the session between nodes and acts on the data PDU. So session management includes setup, yung authentication, termination, and reconnection. Diyan po nangyayari yon sa, nangyayari sa session layer. Okay? Pagdating po sa presentation layer, ito naman po yung primarily responsible for translating data from network data to the formats expected by an application. For example, data encodings and encryption are managed at layer 6. No? Yung nag-encode tayo, yung encryption, it happens in presentation layer. And the higher one, and the last one is the layer number 7, that is application layer. So the application layer includes protocols designed for end users. For example, HTTP, yung Hypertext Transfer Protocol, is a layer 7 protocol designed to transmit data between a web server and a client. So network layer, of course, sometimes we could able to maybe compare the OSI versus TCP/IP. No? Now, the OSI model is only one networking model because another is the TCP/IP model. If we have OSI model, we have also TCP/IP model, which predates the OSI model and maps more closely to the protocols that implement the networking stack. So the TCP/IP model breaks the network stack into 4 layers naman. Ano yon? Nandiyan yung application layer. So in TCP/IP, application layer, this single layer maps to the application, presentation, and session layers of the OSI model. Some protocols that operate at this layer include HTTP, HMTP, and DNS, no, in denial service, no. Then in TCP/IP, we have also transport layer, and this layer maps to the transport layer of the OSI model. TCP and the user datagram protocol operate at this level. Another layer for the TCP/IP is the internet layer. Wherein wala nito sa sa OSI stack, no. Internet layer is equivalent to the network layer naman. Ito equivalent niya pa din sa OSI model sa TCP/IP. So the internet layer is equivalent to the network layer as I mentioned in the OSI model, and this layer is primarily covered by the internet protocol, no. But ARP, AGMP, and ICMP also operate at this layer. And another, of course, in the last under the TCP/IP layer is the network access layer. So this layer combines the physical and data link ng OSI model. Okay? So Ethernet, token ring, ATM, and frame relay are example from the TCP/IP protocol suite that operate at this layer. So the OSI model is more theoretical, describing the various tasks that must be accomplished to enable application layer data to be transmitted via electricity, light, or radio waves. On the other hand, the TCP/IP model is more practical and maps closely to actual network protocols. So what will be the advantages of OSI models? No? OSI provides a mental model for how networking works, including describing all of the various functions that are performed to make network communications possible. And this model makes it easier to troubleshoot issues with network protocols, to examine the security of network protocols, and discuss various network level attacks. We have also the checkpoint solution and the OSI model. So network attacks can occur at varying levels of the OSI model. For example, I think you're familiar with DDoS, no? DDoS or DDoS, no? The distributed denial of service attacks. It can attempt to exhaust network bandwidth layer 3.4 or overwhelm a particular applications with more requests than it can handle layer number 7. We have an enterprise network security architecture. It should have the ability to view and analyze data at all of the host layer ng 4 to 7 kanina, no? Of the OSI model. Ano yung 4 to 7 ng OSI model? Transport, network link, and physical. To learn more about expanding your organization network visibility through the OSI model, you're welcome, of course, to have some available applications which like Checkpoint Quantum Network Security. Okay? Now, what is OSI model explain? No? Again, OSI stands for Open System Interconnection. Kanina pa ang OSI ng OSI, no? This will be a reference model that describe how information from a software application is one computer moves through a physical medium to the software application in another computer. So OSI consists of 7 layers as what we discussed earlier, and each layer performs a particular network function. So the Open System Interconnection Model or the OSI model is a conceptual model created by the International Organization for Standardization or yung ISO na tinatawag natin, which enable diverse communication system to communicate using standard protocols. In plain English, the OSI models provides a standard for different computer system to be able to communicate with each other. So the OSI model can be seen as a universal language for computer networking. It's based on the concept, no, of splitting up a communication system into 7 abstract layer. Each one stack upon the last, no? As what we have here, no, this will be the TCP/IP, no. The Internet Transfer Protocol, no, is the address system of the internet and has the core functions of delivering packets of information from a source device to a target device. So IP or Internet Protocol is the primary way in which network communication are made, and it establishes the basis of the internet. So IP does not handle packet ordering or error checking. Such functionality requires another protocol, and typically the TCP, the transfer protocol. No, the TCP/IP relationship is similar to sending someone a message written on a puzzle through the mail. No, and the message is written down, and the puzzle is broken into pieces. No, each piece then can travel through a different postal route, some of which take longer than others. So when the puzzle pieces arrive after traversing their different paths, the pieces may be out of order. So the Internet Protocol makes sure the pieces arrive at their destination address. And the TCP protocol can be thought of as a puzzle assembler on the other side who puts the pieces together in the right order, asks the missing pieces to be resent, and lets the sender know the puzzle has been received. The TCP maintains the connections with the sender from before the first puzzle pieces is sent to after the final pieces is sent. Actually, IP is a connections protocol, which means that each unit of data is individually addresses and routed from the source device to the target device, no, and the target does not send an acknowledgement back to the source. So that's where protocols such as transmission control protocol come in. Yung TCP it is used in conjunction with IP in order to maintain a connection between the sender and target and to ensure packet order. Let's say, for example, no, when an email is sent over TCP, a connection is established in a three-way handshake is made. First, the source send an SYN initial request packet to the target server in order to start the dialogue. Then the target server then sends a SYN ACK or ACK packet to agree to the process. And lastly, the source sends an ACK packet to the target to confirm the process, after which the message content can be sent. So the email message is ultimately broken down into packets before each packet is sent out into the internet, where it traverses a series of gateways before arriving the target device, where the group of packets are reassembled by TCP into the original contents of the email. Next is the frame This will be the frame header, no? It contains the source and destination address of the frame and the control bytes, no? Payload field, it contains the message to be delivered, and trailer, it contains the error detection and error correction bits. It is also called a frame check sequence. Another, of course, is the TCP dump, no? TCP dump is a packet analyzer that is launched from the command line. So it can be used to analyze network traffic by intercepting and displaying packets that are being created or received by the computer it's running on. It runs on Linux and most Unix X type operating systems at the same time. We have also the IHL in IP header, no? Header length, technically, this is the internet header length, no? It is the length of the IP header in 4-byte 32-bit units known as words and includes any option fields present and padding needed to align the header on the 32-bit boundary. Okay? So we have what we call the version, no? The version will be this field is 4 bits indicated IP version. It always for in IPv4 header, no? So DSCP or differentiated service code point, this field yung 6 bits, no, used to be called TOS, no, type of service, and now renamed to DSCP, no? Ayun yung tinatawag nating from TOS, yung type of service, no, nag-ano siya sa wait lang. As I mentioned earlier, no, yung DSCP as what we have here, no, DSCP is the 6-bit used to be called TOS dati, yung type of service, and now po ni-rename siya sa DSCP, no? DSCP stands for Differentiated Services Code Point, no? And we have also what we call ECN, no? This one, no, ECN. So ECN is explicit congestion notification. This will be actually filled of 2 bits. It is used for end-to-end notification of network congestion. Congestion. It has following, of course, the 00. Yan, makikita natin yung 00 dyan. Capable of transport. No? Yung 10 naman, pag nakita kayo ng 10 dito, ibig sabihin naman yon ECT0 yon. Okay? Kapag 01, yun ay ACT1. Kapag naman 11, ang nakita nyo dito, ay ibig sabihin nun, congestion encountered or yung CE. Okay? So we have a while ago mentioned about the internet header length, yung IHL. No, lagi natin nakikita yung IHL. Ano nga ba yung IHL? IHL is internet header length. So this field 4-bit indicates the length of the IP header and the unit of 4 bytes or 32 bits. So if the value of this field is 5, it means the length of IP header is 20 bytes, no? Because 5 times 4 is 20 bytes, no? Now, the total length, no, this field, no, is a 16 bits indicates the total length of IP packet. No, I think I don't know if you already finished with your network communication 1 or data communication networking. I'm not pretty sure, but I think this will be the prerequisite of the SAM, no. Length of IP header plus length of payload in bytes. So the minimum value is 20 bytes. Since the minimum IPv4 header length is 20 bytes, no? Again, right now meron ng IPv6, no? But I'm now discussing muna yung IPv4. Sa IPv4, ang minimum value niya ay 20 bytes, no? Para clear tayo. Para pag kayo naging system administrator, alam niyo 'yon. So the length of field is 16 bits. So this means the maximum length of one IP packet is 2 raised to 16 bytes, no? Or 65,535 bytes, including the header. So the minimum length of one IP packet is 20 bytes, which is in the case in which there is only IP header and no payload. Now, how about the identification? We have identification. This field is 16-bit is used to uniquely identify a group of fragments that belongs to the same IP program. Okay? Then ang flags naman po natin, yan po yung 3-bit 3-field 3 bits, no? This fields 3 bits is used to control and identify that fragments. The meaning of each bit is, of course, pag bit 0, reversion must be 0. Kapag bit 1, don't fragment. Kapag bit 2, more fragments. So For unfragmented packets, the MF flag is set to be 0. For fragmented packets, bit 0 set to be 0. Bit 1 is set to be 0 and bit 2 is set to be 1. However, in the case of the last fragment of the fragmented packets, all bits are set to be 0. Now, how about the fragment offset? This field is 13 bits indicates the position of fragmented packets from the beginning of the original packet. So the unit is the multiples of 8 bits. Let's say, for example, if the value is 1, it means the fragment offset is 8 bytes. Now, if the value is 10, it means the fragment offset is 80 bytes. So the value of unfragmented packet or the first fragment of the fragmented packet is set to be 0. Now, we have also time to live, no? Meron tayong anong tinatawag na time to live, no? So, this field, no, 8 bits indicate how long the packet can survive in the network. So, even though the unit is in seconds, it is practically interpreted as the number of hops it can go through. So, when the datagram arrives at a router, no, so the router decrements the TTL field by 1. When the TTL field hits 0, the router discards the packet and typically sends an ICMP, time exceeded message to the sender. In this way, we can avoid the situation in which a packet goes round and round within the network within reaching the final destination. Okay, so as what we have here, now we have 60. So you can use it to improve the latency and assure packet delivery of voice, no, over IP traffic. No? So the architecture use a 6-bit value that is defined as differentiated service code point, no, yung DSCP natin kanina, to classify the packet. And the default PHB means that we have a packet that is marked with a DSCP value, yung 00 syempre muna. And this packet should be treated as best effort, no? And so on. Now, we can use the number operator, no, to get the length of the string in bash. No, we have the total length here. So we need to enclose the variable name enclosed in the open and close parenthesis, no, yung ano natin, yung parenthesis natin yun, yung curly bracket natin, no. And inside of that, we use the hashtag, no, to get the length of the string variable. So thus using the hashtag operator in bash, we can get the length of the string variable. Okay? So ganun kinukuha siya. Then for the identifier, sorry. Yon. For the identifier, the thread ID, each of the threads in a process has a unique thread identifier stored in the type thread, and this identifier is returned to the caller of yung pthread underscore create natin na ginagamit sa Linux, no? And a thread can obtain its own thread identifier using pthread underscore self, no? Thread IDs are guaranteed to be unique only within a process, and thread ID is a long positive integer that it created when the thread was created. During the entire life cycle of a thread, the thread ID is unique and remains unchanged. It can be reused when the thread is terminated, and the thread get ID method can study her where we can see how it's used at the same time. If the dot fragment flag, no, ay yung dot fragment flag na natin, bit is set, the internet fragmentation of this datagram is not permitted, although it may be discarded. So this can be used to prohibit fragmentation in cases where the receiving host does not have sufficient resources to resemble internet fragments. So a sender can set the DF or yung don't fragment flag in the IP header, asking intermediate routers never to perform fragmentations of a packet. Instead, a router with a link having a smaller MTU will send an ICPM backward and inform the sender to reduce the MTU for disconnection. The time to live is a mechanism that limits the lifetime of DNS records in the domain name system. Okay? Domain name system stands at DNS. No? It is set by an authoritative DNS server for particular resource record. So the TTL, yung TTL po time to live, is a set in seconds and it is used by caching recursive DNS server to speed up DNS name resolution. The TTL or time to live refers to the amount of time or hops that a packet is set to exist inside a network before being discarded by a router. Time to live or TTL is also used in other contexts, including CDN catching and DNS catching. Okay, so time to live is a field on DNS record that controls how long its record is valid, and as a result, how long it takes for record updates to reach your end users. No? Yun ang gamit ni time to live. I think you are all familiar with protocol, no? Or the TCP/IP, no? TCP is the transmission control protocol, no? A connection-oriented secure protocol. So the data to transmit is sent by the application as a stream of data, then converted by the operating system to the appropriate format. No, modern networking applications require a sophisticated approach to carrying data from one machine to another. So if you are managing a Linux machine that has many users, each of whom may wish to simultaneously connect to remote hosts on a network, and you need a way of allowing them to share your network connection without interfering, no, with each other. So the approach that a large number of modern networking protocol use is called packet switching. Okay? So a packet is a small chunk of data that is transferred from one machine to another across the network. So the switching occurs as the diagram is carried across its link in the network. So a packet switch network share a single network link among many users by alternately sending packets from one user to another across that link. So the solutions that Unix system and subsequently many non-Unix system have adopted is known as the TCP/IP. So when talking about TCP/IP networks, you will hear the term datagram, no, which technically has the special meaning but it is often used interchangeably with packet. Pag sinabi nating datagram, packet. No? And we will also look the underlying concept of TCP/IP protocols. Meron din tayong header checksum. No? The internet checksum, also called the IPv4 header checksum. It is the checksum used in version 4 of the internet protocol, yung IPv4, to detect corruption in the header of IPv4 packets. So, it is carried in the IP packet header and represent the 16-bit result of summation of the header words. So a checksum is a redundant field used by network protocols to recognize transmission errors. And some checksums cannot only detect errors, but also automatically fix error of a certain types. No? The idea behind a checksum is simple. Before transmitting a packet, the sender computes a small fixed length field containing a sort of hash of the data. If a few bits of the data were to change during transit, it is likely that the corrupted data would produce a different checksum. No? Depending on what function you use to produce the checksum, it provides different levels of reliability. Because the checksum used by the IP protocol is a simple one involving sums and ones complement, which is too weak to be considered reliable. Okay? So, different protocols can use different checksum algorithm because the IP protocol checksum covers only the IP header. Most L4 protocols checksum cover both their header and the data. It may seem redundant to have a checksum at L2, no, yung Ethernet. Another one is the LP or L3, yung IP address. And another one is L4, the TCP. Pag sinabi natin L2, Ethernet yon. Pag sinabi natin L3, IP address siya. Pag sinabi natin L4, TCP yon. Okay? Because they often all apply to overlapping portion of data, but the checks are valuable. Errors can occur not only during transmission, but also while moving data between layers. Moreover, each protocol is responsible for ensuring its own correct transmission and cannot assume that layers above or below it takes on that task. No? As an example of the complex scenarios that can arise, imagine that PC LAN 1 send data over the internet PC to PCB in LAN 2, and let's also suppose that the L2 protocol used in LAN 1 use a checksum, but that the one on LAN 2 doesn't. No, it's important for at least one higher layer to provide some from a checksum to reduce the likelihood of accepting corrupted data. The use of checksum is recommended in every protocol definitions, although it is not required. No? Nevertheless, one has to admit that a better design of related protocols could remove some of the overhead imposed by features that overlap in the protocols at different layers. Because L2 and L4 protocols provide checksums, having it at L3 as well is not strictly necessary. No, for exactly this reason, the checksum has been removed from IPv6. No? Kaya nung IPv4, meron tayong checksum. Sa IPv6, tinanggal na siya. Okay? So, the IPv4, the IP checksum is 16-bit field that covers the entire IP header options included. No? So, the checksum is first computed by the source of the packet. And it is updated hoop by hoop all the way to its destination to reflect changes to the header applied by each router. So before updating the checksum, each hoop first has to check the sanity of the packet by comparing the checksum included in the packet with the one computed locally. So a packet is discarded if the sanity check fails, but no ICMPG is generated because the L4 protocol will take care of it. Let's say, for example, with a timer that will force a retransmission if no acknowledge is received within a given amount of time. Another, of course, is the destination in source address. No? Source IP. No? The source IP address for traffic from which traffic is forwarded. No? Yun yung any single address or address range. Destination IP, the IP address of the server to which traffic is forwarded. So, internet port to which port traffic will be forwarded. You can determine the IP address or addresses of your Linux system by using the host name command. Use the -l option. And this example, the IP address is 192.168.122.236. And that is the IP destination address. For IPv4, the destination address can be a host, either network or subnetwork, super network, or the default address. For IPv6, no, okay, the destination address can be host, prefix, or default address. So the default selection specifies default routes, which are the routes that are chosen when no other route exists to a destinations. Na? Then, we display the current ARP cache tables. No? That for all interfaces. The \n parameter is case sensitive. So to display the ARP cache entry for a specific IP address, use ARP/A with the init adder, or yung ating tatawag na ENETADDR parameter, where it other is an IP address. So ARP/A, no, as what we have here, no, yan po ay command used to display the ARP table to a particular IP address. It also known all the entries of the ARP cache to or table. And this command works the same as the ARP_A command, no? Or ARP-D is command used when you want to delete any entry from the ARP table for a particular interfaces. Okay, so we've name dropped the OSI model as required, no? But considered that the simpler 4-layer TCP/IP model may perhaps be a bit more useful. So we've observed that the IPv4 RFC is not lying to us. The information is prescribed is in fact found exactly where it says it should be, no? And I think that's a very useful lesson too, no? You can understand any applications or protocol if you can follow the specification, and the internet RFCs are usually very well written and easy to understand. And I also hope that I showed the Wireshark as useful as it is. It is not some weird sort of unknowable magic, but rather it's just an application of understanding the protocol. I think you've seen how you could build a tool like Wireshark, no, based on what you've learned and at least conceptually. But this only really go as to the IP layer, and we have still a lot of topics left to discuss and coverage the networking. So I'll just want to show you a video presentation with demonstration actually, no, of the discussions of the networking 1-layer, focus on the layers itself.
Hello, and welcome back to CS615 System Administration. This is week 5, segment 1, and we're starting a longer discussion on networking. In the coming videos, we'll dive down into the details of TCP/IP networking on a Unix system. In the process, we'll travel up and down both the 4-layer TCP/IP stack, the 7-layer OSI model, discover just how exactly the Unix system figures out how to talk to other systems, and learn a bit about the physical structure of the internet as well as a few parts of its governance. These videos may well cover parts of topics you've already learned in other classes, but I believe that we should be able to learn something new in each of them still. So why don't we get started with the most familiar layers of the OSI stack. I'm sure you've all seen this before. It's how we oftentimes attempt to represent the different functional parts of a communications network. From the bottom up, we have the physical and data link layers, which in the TCP/IP 4-layer model are combined. Here we're talking about the physical medium and the bitrate, full duplex, half duplex, etc., and the node-to-node transfer of the data using this medium. Then there's the network layer, where we're moving packets between different networks. On top of that is the transport layer, where things start to get a bit shady, because most of TCP fits in here, but TCP also includes features that OSI would classify as belonging in the session layer. But honestly, there's a lot of confusion around what goes into the session and presentation layers, and there's been plenty of criticism of the OSI model. And the dirty truth is that in that so-called real world, you really don't even need to know the details here. Except, for some reason, people like to ask you about it in tech interviews, so make sure to check the Wikipedia page to have the answers they want to hear. The last layer, layer 7, and is the final layer that people like to reference, the application layer. Most distinctions for day-to-day discussions fall into either layer 3 and below, or layer 7. But of course, there are two additional layers that nobody ever tells you about. Layer 8, the financial layer, meaning at some point somebody has got to pay for all the things you're doing over here, and that will influence how you develop things. And then of course you realize that money doesn't come out of nowhere, and that there's yet another layer sitting on top. The political layer. The organization and how it is structured influences how the money is allocated and sets the direction for what is developed, deployed, and supported. And guess what? You're almost always operating on this layer here. We'll get back to the influence of politics, even on a global scale in future videos, but let's leave this theoretical layered model behind for the time being, and look at some actual network traffic to better understand what this model is intended to illustrate. So let's start out capturing some network packets. We do that using the TCP-dump utility, which we start and run in the background, grabbing the port 80 traffic we're interested in this example. With that TCP-dump running in the background, we make a simple HTTP head request to the CS Stevens website. We don't care about the output, we just care about the packets that are collected. Okay, we bring TCP-dump back to the foreground and interrupt it. Change the ownership on the output file, so we can operate on it as a normal user, and then we simply take a look at the first packet captured in this file. We see a lot of information here, and being able to make sense of raw TCP-dump output is a critical skill for system administrators, as we oftentimes have to troubleshoot network connections and protocols. So, what are we looking at here? How does this relate to the OSI model we just showed before? Tell you what, let's first go back to the much simpler TCP/IP stack model. Don't worry, we'll get back to the TCP-dump output in a second. So the TCP/IP model also uses layers, but unlike the OSI model, it only uses 4 layers. And as shown in this illustration, these layers are actually more like layers of an onion, and that each one wraps the other. That is, we're talking about encapsulation, which is nicely illustrated here, where we see that the link layer provides a header and a footer that encapsulates the internet layer, where we're using, in this example anyway, the IP protocol, which adds its header and encapsulates the TCP packet, which finally includes the application data. So let's map these layers to what we're seeing in the TCP-dump output. Okay, so let's look at the details in the hexadecimal output here. The first 24 bytes include the link layer information. The next 2 bytes tell us what type of protocol is encapsulated, IP in this case, which we find in these 24 bytes, with the remainder being the TCP payload. This nicely illustrates how the encapsulation model translates to actual bytes in our packet capture. So let's go ahead and take a closer look at what exactly is in those bytes. The first 12 bytes here are the link layer destination address, with the second 12 bytes as the source address. What exactly are there? Well, our link layer data link protocol here is MAC, Medium Access Control. Our network interface, ZNet0 in this case, has a MAC address as shown here. Since, rather conveniently, the MAC address already is in hex, we don't even have to convert anything. Instead can see it right here in the packet. E07663723900. Okay, so that's our source address, the NIC we're sending the data through. What about the destination address? We can look at our ARP cache table, which keeps the mapping of the MAC addresses to IP addresses on its layer 2 network that it's seen. So here we see that our destination MAC address 001B21735955A maps to the IP address 166.84.7.192, which we can see to be our default gateway. So this makes sense. No matter where we are actually looking to send our IP packet, if it's not on our layer 2 network segment, then we have to hand it off to the default gateway, so it can be routed correctly. And that is why our link layer frame has the destination address of our default gateway. So our default gateway will then take this packet and unwrap the link layer information to look at the IP packet inside. What does an IP packet look like? Well, it looks like this. This is the structure of the IPv4 packet as defined in RFC 791, which then allows us to also look at all the different bytes we observed in the TCP/dump packet and make sense of them. So the first byte here encodes the IP version, 4 in this case, as well as the total length of the IP header, 5 32-bit chunks adding up to 20 bytes, which we see in our TCP/dump output up here. The 5 up here then also tells us that in this case there are no IPv4 options or padding, allowing you to determine where the payload, the TCP data in our case, begins. In the next byte, we encode the Differentiated Services Code Point, or DSCP bits, often used for quality of service assurances, as well as the Explicit Congestion Notification, or ECN field, which in our case is all 0. The next 2 bytes specify the total length of the packet, including the header and data. For us, this is 60 bytes in total, already telling us that the TCP payload is 40 bytes in size after you subtract the 20-byte IP header. Then we have 2 bytes for identification, which is commonly used to identify IP fragments for reassembly if the packet had to be fragmented in transit. Again, that's all 0 for us here. The next 2 bytes again encode 2 pieces of information. The flags, with the don't fragment bit being set here, and the remaining 13 bits used to identify the offset if your packet had been fragmented. Since it wasn't, that's 0, and we end up with hex 4000 for these 2 bytes. Next is the 1 byte TTL, telling us how many hops the packet may at most take. We specify the default, 64 here, which then becomes 40 hex over here. After that comes the byte specifying what protocol the encapsulated payload is. For TCP, we specify 6 over here. Then we have 2 bytes for the IP header checksum, which is a very simple once complement checksum providing minimal corruption protection. For us here, that's hex B903. The remaining 64 bits specify the source and destination IPv4 addresses, which we know to be 32 bits in size each. The source address here is hex 16540763, and the destination address hex 9B F638.0B. Since there are no IP options in this packet, all the remaining bytes in our TCP/dump output up here are thus the TCP payload. But wait, what are the IP addresses? We know what they are in hex, but let's see why we picked these values. We know that these 4 bytes here are the source address, and these 4 bytes the destination address. Let's convert the hex numbers of the source address into decimal. We can use the BC tool for this and set the input base to 16, which then lets us simply enter the hex numbers and it'll spit out the decimal values. So value A6 hex becomes 166 decimal, 54 hex 84 decimal, and so on and so on. Let's look again at our NIC and see what IP address it has. Well, what do you know? Our IP address is indeed 166.84.799. So that's our source address. What about the destination address? Well, since I somewhat frequently have a need to convert addresses like this, I created a shell function to do the translation from hex to decimal for me more easily. The slides have a link at the end to a shell file that contains several of these functions if you're interested. Anyway, so our destination address is hex 9b f6 0b, or 155.246.56.11, which isn't all that surprising, since we had tried to make an HTTP request to www.cs.stevens.edu, which translates to 155.246.56.11, the destination address we observed in the TCP dump output. So we've successfully and completely dissected the link layer and network layer information from the single packet we captured. Congratulations! Now, as you may know, there are other tools that allow you to inspect captured packets. One of them is the popular Wireshark application. If we load our PCAP file into Wireshark with that single packet set, then we can observe all the same data we pulled out of the raw hex bytes we observed. Like before, we find the link layer source and destination addresses over here. The IPv4 information over here, broken down by version, length, DSCP and ECN bits, length identification, flags, offset, TTL, protocol, checksum, and finally the source and destination addresses, as well as the remainder TCP payload. As you can tell, Wireshark is really a useful tool, as it can easily identify all these bits for us, but I do think it's important for system administrators to be able to tease out the information they need using TCP dump, which is why I showed the breakdown one by one in this video. Okay, let's take a break here and recap real quick. We've name-dropped the OSI model as required, but conceded that the simpler 4-layer TCP/IP model may perhaps be a bit more useful. We've observed that the IPv4 IFC is not lying to us. The information it prescribed is in fact found exactly where it says it should be. And I think that's a very useful lesson too. You can understand any application or protocol if you can follow the specification, and the internet RFCs are usually very well written and easy to understand. And I also hope that I showed that Wireshark, as useful as it is not some weird sort of unknowable magic, but rather is just the application of understanding the protocol. I think you've seen how you could build a tool like Wireshark based on what you've learned here, at least conceptually. But this only really got us to the IP layer, and we have still a lot of topics left to discuss in our coverage of networking here, so let's take a look at what's coming next. In the next video, we'll discuss IPv4 subnetting, before we then move on to IPv6 to see how that differs. After that, we'll make a short detour up the stack to layer 9, the political layer, and discuss how the internet is administered and controlled on a very high level, and with a focus on IP space allocation and management. But we'll also talk a bit about the physical structure of the internet. I know, it's all just a series of tubes. Or is it? We'll find out. So until the next time, and thanks for watching. Cheers!
So this will be the references of our discussion for the first topic about networking one, specifically on layers. No? So this time, we may proceed to the networking one, focus on IPv4 basic and CIDR subnetting, no? So the quick definitions, no, subnetting is the process of taking a network and splitting, no, into splitting it into a smaller networks, no, known as subnets. No. It's used to free up more public IPv4 addresses and segments network for security and easier management. Maybe somebody are asking, Doc, why do we need to discuss IPv4 since we have IPv6 right now? Not all the agencies and companies or private organizations are now using IPv6. Most of them are still using IPv4. No, so to understand subnetting, you should first understand the decimal and binary structure of the IP address. No, the IP address looks like di ba yung 192.168.1.20. An IPv4 address is a 32-bit number. So to make addresses more straightforward, they are divided into 4 8-bit numbers or octets, no? O separated by a decimal point, and this octet range is number from 0 to 255, no? And this will be given and discussed during our introduction to computing, no? Wherein you are also able to know on how you'll be able to convert the decimal to binary, binary to decimal, binary to octa, octa to decimal, or vice versa, or octa to binary, and hexadecimal to decimal, hexadecimal to binary, hexadecimal to octa, and vice versa. No? Now, the CIDR is based on the variable length subnet masking, no? The BLSM, no? So the of course the CIDR is based on the variable length subnet masking, which enables network engineers to divide an IP address space into a hierarchy of subnets of different sizes, making it possible to create subnetworks with different host counts without wasting large numbers of addresses. So IPv4 allows for a variation of the network and host segments of an IP address known as subnetting. No, it can be used to physically and logically design a network. So classless interdomain routing, no, yung ibig sabihin ng CIDR, no? CIDR stands for classless interdomain routing. Excuse. So, as a CIDR address looks like a normal IP address, except that it ends with a slash followed by a number. So, the number after the slash represent the number of addresses in the range. Okay, so like 192.0.2.0 is slash 24. That is an example of CIDR. No? So, the address, no, from which a frame or packet of data originates on a network, the source address identifies the sending host to the receiving host, and it is used by the receiving host as a destination address for a response packet, such as an acknowledgement. When begin in communication, the source sends the IP packet to the destination, and the destination returns a response packet to the source address of the IP packet. If the source address is not correct, the destination cannot correctly return as a response, no, sure, source, no, and represent a connection between client and server on the same host. Source and destination port can also be the same. Okay, so the Internet Protocol version 4 or the IPv4 is the port version of the standard that routes internet traffic and other packet switch network introduced in 1982. So by the Internet Engineering Task Force, no, the IETF, no, the AITF, IPv4 is the most widely used version of the protocol despite the limitation of its 32-bit address space. No? So IPv4 or Internet Protocol version 4 is a set of rules that allow service devices, no, like computers and phones, to exchange data on the internet. So each device and domain connected to the internet is assigned a unique number called the IP address. And this address ensures data is routed to the correct device. Now, the IPv4 portion of the address X is called an octet and must be a decimal value between 0 and 255. No? The octets are separated by periods. No? As you can see here, no? 155 period, 2446 period, 56 period. No? So the IPv4 portion of the address must contain 3 periods and 4 octets. No? So we have 1, 2, 3, 4, and 1, 2, 3 periods. No? And IPv4 address is composed of 32 binary bits grouped into 4 octets. The octets are separated by dots. Each individual octet is itself composed of 8 binary digits. No? So if we are going to convert 100111011 into decimal, that is 155. If we convert 111101110 into decimal, that is 246, and so on and so forth. No? Each octet, no, when rendered in decimal format, aids in user comprehension. There are 4 different types of IP address. Meron tayong public, private, static, and dynamic. Na? So IPv4 address have 4 bytes or 32 bits, where IPv6 has 16 bytes. Okay? Ang IPv4 4 bytes, ang IPv6 16 bytes. Na? Pag sinabi natin 16 bytes, 128 bits po yun in length. And these bytes are typically called octets, and for the sake of readability, these bits and octets are written in what's called dotted decimal. So dotted decimal separates each octet of the IP address with a decimal point. Okay? This one, the hexadecimal, no? As you can see here, we have 9B. So it means to say that if we convert 155 decimal into hexadecimal, we could, of course, the answer will be 9B. If we convert 246 to decimal to hexadecimal, that is F6. 56, that is 38, 38 rather, 11 is 0B. No? So the hexadecimal value conversion, we have learned this conversion during our freshman year. Na? Okay, alam na natin yan. Then, IPv4 address are divided into a network part and host part. So an IPv4 address is typically written in decimal digits, formatted as 4 8-bit fields that are separated by periods. So each 8-bit field represent a byte of the IPv4 address. And this form of representing the bytes of the IPv4 address is often referred to as the dotted decimal format. Akala natin nung tayo ay freshman, ano bang gagamitan namin ng conversion? Nagagamit po natin yan sa system administration and network administration. So the network part specifies the unique number that is assigned to your network. So the network part also identifies the class of network that is assigned. No, as what we have here on this figure, the network part occupies 2 bytes of an IPv4 address. Okay, then the host part, this is the part of the IPv4 address that you assign to each host. So the host part uniquely identifies machine on your network. So we need to take note that for each host on your network, the network part of the address is the same, but the host part must be different. In networking, actually, a broadcast means that we send something that everyone receive, whether they need or want it or not. Switches will forward broadcast traffic on all their interfaces, except the one they receive the broadcast on. So broadcast traffic is not very efficient. Let's say, for example, let's say that the ARP request is sent by H2 to figure out the MAC address of H1. So the information in the ARP request is useless for SW2, SW3, and H3, as what we have here. Okay, but they do receive it. SW2, ito po, and SW3 have to waste bandwidth, forwarding the broadcast frame to H3, dito, because it wastes some CPU cycles to look at an ARP request that it doesn't care about. Nowadays, CPU are fast and we use fast, yung gigabit interface, so that impact of broadcast traffic is not so bad. about 20 years ago, having a network with a lot of devices could impact your performance because of broadcast traffic. Older operating system also use a lot of broadcast traffic for their applications because broadcast domain with 1 to 1,000 devices are common nowadays. No? Still, a single device that sends a LOT of broadcast traffic does affect the entire broadcast domain. So it's good idea to limit the size of your broadcast domains. No? So there are three different IPv4 networks, no, classes. No? Currently, there are three classes of TCP/IP networks. Each classes use the 32-bit IP address space differently, providing more or fewer bits for the network part of the address. And these classes are Class A, Class B, and Class C. Familiar kayo dyan, ano, kung kayo nag-networking na. No? IPv4 addresses are categorized into the three basic, yung unicast address, multicast address, and broadcast address. No? So in the IPv4 IP address space, there are 5 classes. We have A, B, C, D, and E. And each class has a specific range of IP addresses and ultimately dictates the number of devices you can have on your network. Primarily, Class A, B, and C are used by the majority of devices on the internet. Class D and E are for special uses. And the 5 available IP classes, along with the number of network, each can support the maximum number of hosts or devices. That can be on each, can support the maximum number of hosts, no, in each those networks. So the 4 octets that make up an IP address are conventionally represented by A, B, C, D. Okay, such as 1.127.10.20.30. Okay. Additionally, no, information is also provided on private addresses and loop address no used for network troubleshooting. Pag sinabi natin Class A address are for networks with large number of total hosts. Class A allowed for 126 networks by using the first octet for the network ID. So the first bit in this octet is always 0. Okay? So the remaining 7 bits in this octet complete the network ID, and the 24 bits in the remaining 3 octets represent the host ID and allows for approximately 17 million hosts per network. Class A network number values begin 1 and end at 127. For Class B addresses are for medium to large size networks. So Class B allows for 16,384 networks by using the first 2 octets for the network ID. The first 2 bits in the first octet are always 1 and 0. And the remaining 6 bits together with the second octet complete the network ID. The 16 bits in the third and fourth octet represent host ID and allows for approximately 65,000 hosts per network. Class B network numbers value begins at 128 and ends at 191. For Class C addresses are used in small local area networks. Class C allows for approximately 2 million networks by using the first 3 octets for the network. Okay, first octet are always 110, and the remaining 21 bits of first 3 octets complete the network ID. And the last, of course, octet 8 bits represent the host ID and allows for 254 hosts per network. Class C networks number value begins 192 and end at 223. Okay? Now, the Class D, yun ang Class A, ano natin yung Class A and B. Ito po yung sinasabi ko kanina, no, subnet networks. Ito po yung host per networks na sinasabi ko. Accept. Yan. Now, as what we have here, we have Class A, Class B, Class C, Class D, and Class E. No? For Class D, IP address are not allocated to hosts and are used for multicasting. So multicasting allows a single host to send a single stream of data to thousands of hosts across the internet at the same time. It is often used for audio and video streaming, such as IP-based cable TV networks. Another example is the delivery of real-time stock market data from one source to any brokerage company. So ang Class D, most commonly used in video and audio streaming. Or kaya naman sa real-time stock market. Okay? Class A, IP address are not allocated to hosts and are not available for general use. These are reserved for research purposes. So, within each network class, no, there are designated IP address that is reserved specifically for private internal use only. So, the IP address cannot be used of internet-facing device as that are not routable. Let's say, for example, no, web servers and FTP servers must use non-private IP address. However, within your own home or business network, private IP addresses are assigned to your devices, such as workstation, printers, and file servers. So, a subnet mask, no? Subnet mask is used to divide an IP address into two parts. So one part identifies the host and the other part identifies the network to which it belongs. So to better understand how IP address and subnet mask work, you need to look at the IP address and see how it's organized. So the subnet mask signifies which part of the IP address is network and which part is host. So the subnet mask is compared to the IP address from left to right, bit for bit. And the ones in the subnet mask represent the network portion and the zeros represent the host portion. Kung makikita po natin dyan. So, there are networks shown known as classful and classless. The first plan, of course, is to adapt the use widely by internet community. We're classful networks. So, named because three addresses classes, A, B, and C, were defined with assignable IP address space. And these classes, however, disproportionately distributed the number of available IP addresses. So a new method to identify networks and allocate IP addresses was needed to support the continued growth of the internet. The new method is named classless because it does away with the idea of class together. It is commonly known as classless inter-domain routing, yung CIDR natin. It is much more flexible than classful network, and it is what the internet uses today. Classful networks are still used by many devices, so it's important to understand both classful and classless networking. So yung class B na ginatawag natin, address requested 64 and 48 hosts, it needed 244 addresses. Ganun karami ang kailangan ni class B. For the CIDR cheat sheet, no, also known as supernetting, it is a method of assigning internet protocol addresses that improves the efficiency of address distribution and replaces the previous system based on Class A, Class B, and Class C networks. So CIDR notation replaces the former address and subnet mask combination. So the slash suffix describes how many bits are used for the network mask, and the remaining bits are reserved for the host address. Classless inter-domain routing was developed to provide more granularity than legacy classful addressing. Mask expressed in the form of /XX are in CIDR notations. No? So this will be the summary. No? The classful networking largely for historical contents and classless inter-domain routing or the CIDR. Okay, this will be the link. And I'll just want to play the demonstration of the IPv4 basic and CIDR subnetting.
Hello, and welcome back to CS615 System Administration. This is week 5, segment 2, and after we looked at the details of the IP packet in the last video, I think it's time we quickly rehash some of the basics of IPv4. So in this video, we'll take a look at what exactly an IPv4 address looks like and how we sort out where on the network it is placed. We'll discuss the concept of classful networking from the early days of the internet, as well as the ubiquitous subnetting approach known as classless inter-domain routing or CIDR. Remember, in our last video, we looked at this illustration of the network packet with respect to the IP protocol, and we noted that it contains two IPv4 addresses, the source address as well as the destination address. The destination address in our example was 155.246.56.11, the address of the Stevens CS web server, which in our IP header of course was represented as binary digits. Which gets us to our very first and rather basic observation. IPv4 addresses are 32-bit numbers, meaning we have exactly 2 to the 32 possibilities for the entirety of the IPv4 IP space, something that we'll get back to in our next video when we talk about IP exhaustion in IPv6. So our IPv4 address is a 32-bit binary number, but a 32-bit binary number is somewhat unwieldy and hard to remember, which is why we commonly divide these 32 bits into 4 octets. Each of these octets is then represented with a decimal value and separated by a dot, leading to the common dotted decimal representation of the IP address, or 155.246.56.11 in our example here. Although of course we can represent the octets in hex as well if we like. We've seen this being done in the TCP dump hex output, where the destination address did indeed show up as exactly 9BF638.0B. But how does this 32-bit number, even if divided into 4 octets, help us understand where on the network the address might be, or what other systems it might be able to talk to? To understand that, we note that each IP address is divided into a network and a host component. Here we observe that the first 16 bits represent the network portion of the address, and the last 16 bits the host portion. But what does this mean, the network portion? Well, hosts in the same network can communicate with one another without the help of a router. We call this being within the same broadcast domain, and it's an example of the difference between layer 2, the network layer, and layer 3, the transport layer. A packet addressed to a host in the same layer 2 network can be delivered by a network switch. If the host is on a different network, then you need a layer 3 capable device, such as a router. How do we know what the network portion of an IP address is? In the early days of the internet, all you had to do was look at the first 3 bits of the address, which could tell you exactly which class of a network the address was on. So we had a total of 3 classes of networks, known as a Class A, a Class B, and a Class D network. Except, of course, there were really 5 different classes you could identify by inspection of the first 4 bits. Specifically, if the 32-bit IP address started with a 0, then you knew you had a Class A network, where the first 8 bits comprised the network portion of the address, meaning you had 24 bits remaining for the host portion, allowing you to address 2 to the 24, or over 16 million hosts within the same broadcast domain. If the first 2 bits were 1 and 0, then you had a Class B network with 16 bits of network portion and 16 bits used for the host portion. If the first 3 bits were 1, 1, and 0, then you had a Class C network with 24 bits of network, 8 bits host portion. But then we also have the Class D and E networks, where Class D is reserved for multicast addresses, and Class E was early on reserved just in case. Remember, IPv4 was intended to be an experiment, and so we reserved a chunk of addresses for future use, the Class E network shown here. But okay, so if you had a Class B IP address, that meant that you had 16 bits network portion and 16 bits host portion, meaning you were on the same broadcast domain as about 64,000 other hosts. That's one big network. Chances are you didn't need such a large network and would have preferred to have a smaller network. So instead of just looking at the IP address and dividing the network and host portion based on the first few bits, we then introduced the concept of a net mask. That is, we added a second 32-bit number that was used to mask certain bits in the original address. All the bits that were 1s would represent the network portion, and all the bits that were 0 would represent the host portion. Now the advantage of this was that even if you had such a Class B network IP address as the one shown here, you can then divide that network further into smaller networks, subnets, by picking a different net mask. Here we show a 24-bit net mask, leaving 8 bits for the host portion, effectively taking the Class B network and creating a Class C subnet within this network. The 24 bits that are 1s here are then denoted in the network in so-called slash notation, as /24, although we can represent this net mask in decimal notation as well, yielding 255.255.255.0 in this case. You've probably seen this net mask before, so it's a fairly common one, since it creates a reasonably sized network while at the same time making it easy for humans to quickly identify where this network begins and ends, namely exactly at the quad-dotted boundary. But the net mask doesn't have to align with the decimal dot boundaries. After all, it's really just a sequence of bits, so if we wanted to create a smaller subnet, we could, for example, use a /26 network, 255.255.255.192 in decimal. Or, if we had a need for a larger network, we might use a 22-bit network. Fortunately for us, we don't need to perform this logic in our head. After all, computers are much better than humans when it comes to manipulating numbers, and especially binary numbers, so there are all sorts of convenient tools that can help you identify the right net mask. For example, we have the ipcalc utility, which you can install from your favorite package manager. If we pass it our IP address and the net mask in slash notation, using /16 in this example, then we get back output like this. It shows us the 16 bits of the network portion in the net mask being set to all ones. But it also tells us that this was originally a class B network address, based on inspection of the first 2 bits. With 16 bits left for the host portion, we now know how many hosts we can have on the subnet, almost 64K. But with 16 bits left, we should be able to get 2 to the 16 hosts, or exactly 64K. But we are losing 2 entries, because the first and last addresses on the network cannot be assigned to a host. The first address is the network address itself, and the last address is the so-called broadcast address, where if a packet is sent to this address, it is broadcast to all hosts on the network. So if we adjust the net mask to a /24, then we get the adjusted information as shown here, with 24 bits of network portion and 8 bits of host portion, yielding 2 to the 8 minus 2 possible host addresses. A /26 then looks like this. 26 bits for the network portion, 6 bits for the host portion. But ipcalc can do more for us. Suppose you want to take a network and create subnets of different sizes. Let's say you want to carve up an existing /24 into one subnet able to contain 24 hosts, one for 64 hosts, and one for 48 hosts. What would be the right net masks for that? Let's ask ipcalc. It shows us that for the first network, we'd use a /27, able to hold 30 hosts. For the second subnet, we need a /25. And for the third subnet, we'll need a /26. ipcalc also shows us that we still have some network space left. We could create another /27 with the remaining IP addresses. So, what ipcalc showed us was that the calculations of the serial notation all follow the same logic. Let's assume you have an IP address abcd/n, 155.246.1156/27, let's say. Then we know that n represents the number of bits in the net mask that are all ones, describing the network portion, i.e. 27 in this example. The total IP address length is 32. So the remaining bits available for the host portion are 32 minus n, or 32 minus 27, i.e. 5, in our example. The total number of addresses available here is then 2 to the power of that number, or 2 to the 5 equals 32 in this example. But we know we can't use all of them, as we have to subtract 2, namely the first address of the network address itself, and the last address of the network, the broadcast address. Finally, the net mask, being just another 32-bit number, can also be represented as a decimal quad-dotted address. Alright, time for another break. In this video, we briefly mentioned the historical context of class 4 networking. This is not used any longer, but it's still useful to understand, as always. We then talked about the concept of dividing a network into smaller networks, i.e. subnets, through the use of a net mask, and we identified the different logical steps in this process. Now all this applies to IPv4, but what about IPv6? Well, we'll talk about that in our next video.
So as I mentioned earlier, we already shared that right now we have IPv6. So IPv6 is the next generation internet protocol standard, intended to eventually replace IPv4, and the protocol many internet services still use today. As I mentioned earlier, hindi pa lahat kasi ng private organizations ay gumagamit ng IPv6. Meron pa ring IPv4. That's why I also included IPv4 earlier. Now, every computer, mobile phone, and any other device connected to the internet needs as a numerical IP address, in order to communicate with other devices. So the original IP address scheme called IPv4 is running out of addresses. So an IPv6 address is at 128-bit alphanumeric value that identifies an endpoint device in an Internet Protocol version 6 network. So IPv6 is the successor to a previous addressing infrastructure, IPv4, which had limitations. IPv6 was designed to overcome. Notably, IPv6 has drastically increased address space compared to IPv4. So the Internet Protocol is a method in which data is sent to different computers over the internet, as what we discussed earlier. Each network interface or computers on the internet will have at least one IP address that is used to uniquely identify the computer. So every device that connects to the internet is assigned an IP addresses, which is why there was a concern with the number of IP addresses in IPv4 and why the Internet Engineering Task Force, yung IETF, defined as the new IPv6 standard. Operating systems like Windows 10, 11, Mac OS, and Ubuntu support IPv6. Currently, accept. The use of address types is mixed. Devices is in use now will either use IPv4 or IPv6. Domain name systems have supported IPv6 since 2008, imagine. So it has been a concern for some time that the IPv4 addressing scheme was running out of potential addresses. So the IPv6 format was created to enable the trillions of new IP addresses to connect an ever greater number of computing devices and the rapidly expanding numbers of items with embedded connectivity. And thanks, of course, we need to thank the Internet of Things, the IoT. The number of potential IPv6 addresses has been calculated to be over 30 or 340 undecillion or 340 trillion. According to computer history, the number allows an IPv6 address for each atom on the surface of the planet with enough leftover for more than 100 more similar planets. Imagine that. So what will be the format of the IP6 address? In precise terms, an IPv6 address is 128 bits long and it's arranged in 8 groups. Each group is 16 bits. Each group is expressed as a 4 hexadecimal digits and the groups are separated by colons. So as what we have here, we have the source address also, same with the IPv4. We have the destination address, and so on. So this will be the development snapshot of NetBSD for testing, no, for this IPv6 basic, no. This will be the one using the TCP dump, as what we did in our IPv4 also. But there are certain changes now when it comes to iConfig, CNET 0, grep init 6, and so on. And the source address and destination address from the version to traffic class, flow label, payload load, next header, and hook meet, no? And the DSCP default is 0x00. Okay? Then we have 20-bit flow label, na yung RFC637, and the BCC6 B66C rather, no, for the terminal 80 by 24. Of course, the payload length at the same time, and the protocol that TCP is equal to 0 times 06, no, and of course the destination, the source address and destination address. In IPv6, no, we have 2001-499.124:1507:F006. As you can see, there are combinations of hexadecimal value, no? So now, the IPv6 uses 128 bits or 2 raised to 128 addresses following the 3.4 times 10 raised to 38 unique IP addresses. And this is equal to 340 trillion IP addresses. Ganun karami, no? Ang kayang ma-handle na IPv6, no? IPv6 is written in hexadecimal notation separated into 8 groups of 8 bits by the colons. Thus, 8 times 6 is equal to 128 bits in total, no? The main advantage of IPv6 over IPv4 is its large address space. So the size of IPv6 address is 128 bits compared to 32 bits in IPv4. So the address space therefore has 2 raised to 128 or, naku, ang haba. Okay? Basta trillion addresses, no? 3.4 times 10 raised to 38. No, in precise terms, an IPv6 address is 128 bits long and it is arranged in 8 groups, each of which is 16 bits. Each group is expressed as 4 hexadecimal digits and the group are separated by colons. So an IPv6 address is split into 2 parts. No, ganun din. Network and a node component. Okay? So as you can see here, no, pag sinabi nating 0100100110011000, that is 4998, no? And so on and so forth. So yung 11110000000000 is F00 yan in hexadecimal value. Then this will be the IP address consist of 8 16-bit fields in case insensitive, hexadecimal, and colon separated words, no? Leaving zeros in a field are optional, no? The panel list of field formatting in data create attributes. You can modify the width of a field for TABL formatting. Leaving zero suspension for numeric fields, you can also specify data create attributes, no? The panel comes in 2 flavors, one for alphanumeric fields and one more for numeric fields. This section describes the numeric field version. Okay, so successive fields of 0 represented as colon, but only once in address, no? Ganyan po yung magdi-display. Kapag naman po 0 represented, no, but only once in an address, ito po siya. Then of course 2031. Then this will be the 0030F and 130B, no, for the IPv6 also. Okay, then later on I will show you on how we'll be able to do that. Now, so in a special case, now cases, no, look back address that is colon 1, the IPv4 map addresses that is colon FFFF colon 74.6.1.3.25, but separating IP and port now requires bracket, no? Ito na yung nasa baba, no? So meron tayong bracket for IPv6. So IPv6 address scope, link local, unique local, and global. So kung dun sa ating programming languages, meron tayong sinasabi na merong application ng global, local, and unique variables. So dito rin sa networking, specifically for IPv6, meron din tayo. So explore IPv6, that's your ISP, provide your ISP IPv6 address, that's your local Wi-Fi access point. Ito po yung mga ano natin, dinidiscuss natin or kailangan natin matutunan. Okay? So this will be the link for IPv6 discussion, and this will be a demonstration of the use of IPv6.
Hello, and welcome back to CS615 System Administration. This is week 5, segment 3, and following our analysis of the IPv4 packet and the concept of classless interdomain routing or CIDR subnetting, it's time to now take a look at our big hero IPv6, coming to rescue us from IP exhaustion. So, to refresh our memory, let's look real quick at this illustration from a previous video, showing the structure of the IPv4 packet, where we identified the various segments based on a single TCP packet captured using TCP dump while talking to the StephenCS web server. We had called out the 32-bit source and destination addresses, and looked at how a subnet mask can be used to divide the address into a network and a host portion. So now, what does this look like when using IPv6? For that, we'd like to repeat the previous packet capture, only this time we'll make a request to a website that has an IPv6 address. Note that you do of course need to be on an IPv6 enabled system to repeat this exercise. Your home ISP may or may not offer you an IPv6 address, and your local Wi-Fi access point may not be configured to offer IPv6. Unfortunately, it's 2021, and Amazon still does not enable IPv6 by default on all your resources. But at least since 2017, you can actually get a native IPv6 address in AWS and don't need to use a tunnel broker, so hooray for progress. Anyway, so if you want to ensure your new AWS instances comes up with both IPv4 and IPv6 enabled, also known as being dual stack, you can follow the steps I outlined here in this blog post. With that, your instance should then get a routable IPv6 address, so we can then start our packet capture. Okay, so we again start out with TCP dump. This time looking for packet communicating with www.yahoo.com. We make our curl request as before, and then read the first packet we captured from the file. Now, the first few bytes are going to be the same, since this is on the data link layer using the same MAC address as we did before. But then the next field, describing the type of the protocol the MAC frame wraps, is no longer IP, but now the value for IPv6. The bytes starting after that, and going up to about here, are the IPv6 header, with the remainder as the TCP payload. Let's look at our IP addresses on the ZenNet 0 interface, and what www.yahoo.com resolves to, so we can compare that output to what we find in the TCP dump packet. Okay, there we go. Now let's compare to what we did for IPv4. Here's the structure of the IPv6 header, which looks similar, but a bit simpler than the IPv4 header, don't you think? Let's look at the fields. First, we have a 4-bit version field, which is set to 6, no surprise. Next, we have the traffic class, which, similar to an IPv4, includes the DSCP and ECN bits, all 0 here. After that comes a 20-bit flow label. A flow is really just a group of packets that belong together, such as, say, a TCP session. By having this identifier, we can later more easily trace a full request across the network. Anyway, so this flow label is generated randomly, and the first 32 bits here are represented in the above 8 hex bytes. Next comes the payload length, 28 hex or 40 decimal, since we have no additional IPv6 headers here. Then we specify the protocol of the payload, TCP in this case, and add a hop limit, effectively the TTL we recall from the IPv4 header, with a default value of 64 just like in IPv4 as well. And that's really it. The remaining 256 bits are used for the source address and the destination address, highlighted here in the TCP dump output in hex. Okay, so now do we have to go back to the tedious task of converting these hex characters into an IP address as we did for IPv4? Take a look. Turns out we don't. IPv4 addresses are in hex, so we see our actual IP address here, literally in the TCP dump packet, which is rather convenient. Now let's again compare to IPv4. As we observed in our last video, IPv4 addresses are 32-bit numbers, and as we've seen, IPv6 addresses are a bit larger. Specifically, IPv6 addresses are 128-bit numbers. Why we ended up with 128 bits, and what problems IPv6 was intended to solve, is something we'll cover in our next video. But for now, let's focus merely on the structure of the address. And so having 128 bits makes for a rather unwieldy long address. If we used the dotted decimal notation, we'd end up with 16 octets. So instead, we use 8 16-bit fields that we convert to hex and separate by a colon, so that our really long bit string here becomes this hexadecimal string. But since strings like this can still be a bit large, we have a few ways of shortening them. For starters, any leading zeros can be left out. But in addition, if we have successive fields of zeros, then we can leave those out completely. But note that we can only do this once, meaning that if we had double zeros on the left and on the right, you have to decide which ones you want to compress. So for example, if you had an address like this, then you could either compress it like this, by eliding the 2 leftmost 0-bit fields, or you can compress it like this, eliding the 3 rightmost 0-bit fields. But note that we cannot compress both sides, since now it's impossible to determine how many fields should be filled in on the left or right. But do note that either of these two compressions, right only or left only, are valid and represent the same address, as does the uncompressed version of the string. Okay, so in addition to the compression of the string, there are a few additional things you want to consider when it comes to written IPv6 addresses. Just like in IPv4, where we have 127.0.0.1 on the loopback device, we also have an IPv6 loopback address, : 1. Note that this is really not a special case at all. It is merely an address with 127 leading 0 bits, translating to 7 words of all zeros, which we compressed. The bigger difference here is that the loopback device in IPv4 actually got an entire Class A network, not just that one address, but we'll get back to that in a future video. If your system is dual stack configured, and your socket allows both IPv4 and IPv6 addresses, you may encounter so-called IPv4 mapped addresses, where the 32-bit IPv4 address in dotted decimal format is stuffed into an IPv6 address with a special prefix of all zeros FFFF. Next, although not strictly part of the IP address, we have to consider how applications handle specifying a port in addition to an address. In IPv4, we use the : port notation to specify an IP address port pair, but since IPv6 addresses use the colon as a separator, we can't do that. For that reason, we use a new syntax, where we use brackets around the IPv6 address followed by a colon and the port. Finally, we need to point out that different IPv6 addresses have different implicit scopes. As you may have noticed when we looked at the output of ifconfig, we noticed that each interface has multiple addresses. So far, that's not unusual, as any interface can have multiple IPv4 addresses too. But in IPv6, each interface always has a so-called link local scope address. This link local address is generated on the host itself without requiring any specific network knowledge or DHCP help or anything like that. It is an address within the FE80/10 network, with the low 64 bits generated using a standardized algorithm. This address is only used on this specific link, and any packets received or sent to or from this address are never forwarded to any other link, meaning you are guaranteed that the packets stay on the interface. Next, we have so-called unique local addresses in the FC00/7 network, which are used for private IPv6 networks and which are not globally routed. This is conceptually similar to the IPv4 RFC1918 IP space that you're familiar with from your local Wi-Fi network, your AWS default IPv4 space, etc. Lastly, we have the global addresses. These are the normal addresses you will see and use, such as the one we used in our examples here. They are globally unique and can be routed on the public internet. Now, as you can see from looking at these bullet points here, we frequently talk about network space in terms of slash notation, just like we did when we talked about IPv4 CIDR subnetting, and that's one of the things where IPv6 really is not that different from IPv4. We still use a bitmask called a subnet prefix here, and the slash notation still applies. The only difference here is that the number after the slash can be a lot larger, since we now have 128 bits to play with. So it should come as no surprise that we can use similar tools to calculate and inspect the different subnet prefixes. The ipcalc utility we used in our last video doesn't support IPv6 unfortunately, so we are using a different tool, sipcalc. If we specify a /64 subnet length, then we get output like this, illustrating the expanded and compressed forms, as well as the subnet prefix, the address scope, and the network range, all looking rather similar to our previous IPv4 examples. If we wanted to increase our subnet, we'd use a smaller network prefix, say /48 here. And if we picked a /72 prefix, things would look like so. Note, however, that one of the most commonly encountered prefixes will be /64. Why that is something we'll cover in our next video. Alright, so now it's your turn to look around and explore the IPv6 world around you. Check if you get an IPv6 address, and if so, whether your normal network is IPv6 enabled. This can extend to common public networks or your home network. If your home network currently doesn't support IPv6, can you change that? What about our AWS instances? I already linked the blog post that describes how you can set up your environment to ensure your instances come up dual stack. If you haven't done so already, please do that now, as we'll be using dual stack networking in our next videos and exercises. Do some research and find out which popular services and systems are IPv6 enabled. You may assume that all the big players would be, but are they? Which services are not? Why do you think that is? In our next video then, we'll talk a bit about internet governance and discuss where IP addresses come from, how they are allocated, and why exactly we even need IPv6 at all. 32 bits should have been enough for this little experiment called the internet, no? Until the next time, thanks for watching. Cheers.
Okay, so we have the segment 4, that is networking 1, IP allocation and exhaustion. So we are going to discuss this IP allocation and exhaustion in IPv4 and IPv6 at the same time. No, again, hindi kasi lahat ng government agency, private industry ay IPv6 na. Kaya kailangan may background pa rin tayo sa IPv4. Okay, so IPv4, no, exhaustions, a problem resulting from the unanticipated popularity of the internet at the time of its creation. So it's the depletion of available IPv4 addresses for connected devices. Beginning in the early 1980s, each computer was assigned a unique public IP address consisting of 4 groups of 8 bits or 32 bits total, and this is standard called IPv4 as what we discussed earlier. At the time, this supply seems inexhaustible, but by the late 1980s, it was already clear that even a pool this large would inevitably run out. with the rapid expansion of internet users, always on device, mobile device, and right now the IoT, that time is now upon us, no? The pre-pool of IPv4 addresses managed by regional enterprise internet registries or RIR, no, have been fully allocated, no? And the regional internet registry served the US, Canada, and several Caribbean and North Atlantic island was fully depleted in September 2015. So that's why beginning in 1990s, a series of new technologies were developed to address the looming problem of IPv4 exhaustions. And IPv6 introduced a successor of IPv4 using a 128-bit address. So IPv6 offers a full dozens of orders of magnitude larger than IPv4, and it is practical purposes in exhaustible. No? However, IPv6 is not backward compatible with IPv4, making direct communications between the two impossible without some intervening technology. So, in the meantime, no, IPv4 exhaustions possess critical problems for internet users and service providers that depend on IPv4. Any shortage or delay in IP address assignment to a device from a network can result in the degradations or even outright denial of service to the subscribed device. No? With extensive investment in IPv4, organizations also need to be able to extend the value of their existing infrastructure while making a staged IP address IPv6 migration over time. Again, it is important to consider the compatibility of your infrastructure in IPv4 to IPv6. One approach is network address translation or yung NAT. It involves remapping an IP address space into another, making it possible for a single IPv4 address to be used for an entire private network rather than having a separate IPv4 address assigned to each device within the network. We have what we call carrier grade NAT, also known as large scale NAT, or served as a similar functions on a carrier level, making it possible for a small pool of public IP addresses to be shared across a large number of end sites. No? So this will be an IP address for 32-bit numbers, no? As what we discussed earlier. And the Internet Assigned Numbers Authority, as I mentioned earlier, no, the IANA covers global IP address or AS number allocations, route zone management also. So the Regional Internet Registry or RIR is a non-profit organization that manage internet number resources within a geographical region. Now, 5 RIRs operate in 5 regions across the globe in total, including APRINIC, APNIC, IRIN, LACNIC, or yung tinatawag nating APRINEC, APNEC, AREN, and LACNET, and RIPE, no, NCC. A regional internet registry is an organization that manages the allocation and registration of internet number resources within a region of the world. No? Internet number resources include IP addresses and an autonomous system numbers or yung AS natin. So, the regional internet registry system evolved, eventually dividing the responsibility for management to a registry of each 5 regions of the world. So, the regional internet registry are informally liaised through the Unincorporated Number Resource Organization, yung NRO, which is coordinating body to act on matters of global importance. No? Regional internet registries are components of the Internet Number Registry System, which is described, of course, in the IETF RFC 7020. So the Internet Assigned Number Authority delegates internet resources to the RIRs, who in turn follow the regional policies to delegate resources to their customers, which include internet service providers and end users organizations. Collectively, the RIRs participate in the number resource organizations, form as a body to represent their collective interests, undertake joint activities, and coordinate their activities globally. So the NRO has entered into an agreement with ICANN for the establishment of address supporting organization, which undertakes coordination of global IP addressing policies with the ICANN framework. Ay parang wala na tayong pakialam dyan, no? Pero sila ang in charge, no, for the IP addresses. So the NRO or Number Resource Organization is an unincorporated organizations uniting the 5 RIRs. Na it came to exist at October 23, 2003 with the 4 existing IRRs entered to a memorandum of agreement in order to undertake joint activities, including joint technical projects and policy coordinations. Na then this will be a host route, no, with the Glue network and identifying the LIR and ISP. So based on John Schwarzman, no, don't believe there's nothing as permanent as temporary solution. Ben Cert chose 32 bits for IPv4 in 1976, enough to do an experiment. That is way back 1976, but right now not capable na siya. So this will be the private IP space, no, for IPv4 exhaustion. Approximately 10 to 13% of the entire IPv4 space. So the IANA address pool exhaustion, AppNet, RIPE, NCC, LACNEC, AREN, AF, or APRINEC, no? And this will be the IPv4 was introduced in 1995, no? So this will be the single end user LAN, default and site assignment, no? And the local internet registry. Ito yung LIR natin, and the regional internet registry allocations from AINA o yung RIR natin. Okay? So the IPv4 address are 32 bits number, meaning we can have 2 raised to 32 IP addresses. No? This will be an example of a computer expert level answers of a breakthrough algorithms knowledgeable in artificial intelligence technology. Actually, this will be an activity, no? This will be the references, and I'll just want to play a video presentation and demonstration of the IPv4, specifically IP locations and exhaustions.
Hello, and welcome back to CS615 System Administration. This is week 5, segment 4, and so far we've covered a fair bit of ground with respect to the IP protocol, having looked at the details of the IPv4 and IPv6 headers. But we've avoided the difficult question, Mommy, where do IP addresses come from? And just why do we have an IPv4 and an IPv6 address? And wait a second, what happened to IPv5? Alright, let's quickly resolve that last question, because that's easy. There is, in fact, an IP layer protocol using protocol version 5, the Internet Stream Protocol. And yes, logically, there also were in fact protocols versions 1, 2, and 3, with version 3 being the first version in which TCP and IP were split. But let's get back to IPv4. As we said, an IPv4 address is a 32-bit number, meaning we can have exactly 2 to the 32 such numbers. 2 to the 32 is a large number, and so the entire IPv4 internet address space is approximately 4.3 billion IP addresses. Well, at least that's the theoretical space we have. Now, how do you go about getting one of those? As you may know, many systems come up and seemingly magically acquire an IP address via, e.g., DHCP. Where do they get that address from? Let's take Stevens, for example. How did we end up with almost all our IP addresses beginning with 155.246? To answer that, let's take a short trip back in time to the early days of the Internet, when IP address space management, and much more, lay in the hands of just one man, more or less, Jon Postel. Jon Postel was an immensely influential person in the development of the Internet, and initially administered the Internet Assigned Numbers Authority, or IANA, meaning when an organization needed to have IP space assigned, he took care of this. He also co-authored a significant number of RFCs, including those that became the foundation of the domain name system, which we'll revisit in a future video lecture. But obviously, having any one person in charge of IP address space allocation is not a scalable solution, and so the administration of IANA was transferred to ICANN. Now, I'm really glossing over an incredibly impressive history of one of the biggest internet pioneers and architects, so I strongly recommend you read up on Jon Postel on your own. You likely have heard of Postel's Law, also known as the robustness principle in software programming. Be liberal in what you accept and conservative in what you send. This too is named after Jon Postel. But okay, so we now have IANA, a non-profit standards organization which oversees global IP address and autonomous systems number allocation, root zone management, etc. We'll revisit these areas in future videos, but for today we'll stay focused on the management of the IP spaces. So IANA is in control of the IPv4 and IPv6 spaces, meaning it can take out large net blocks and assign them to other entities. Now you'll note that I have illustrated the IP spaces as missing certain parts that are not available to IANA to hand out, which is because for both IPv4 and IPv6 there are certain net blocks that are reserved for special purposes, such as the RFC 1918 private IP space you're all familiar with and its IPv6 equivalent. Anyway, so of the net blocks that remain available, IANA may then assign large chunks to the regional internet registries, such as the African Network Information Center, or AFRINIC, the Asia Pacific Network Information Center, or APNIC, the American Registry for Internet Numbers, or ARIN, the Latin America and Caribbean Network Information Center, or LACNIC, and the Réseau IP Européen Network Coordination Centre, or RIPE-NCC. Each of these RIRs manages the allocations for a specific geographical region, which illustrates the distributed nature of the Internet, despite its obvious US origins. By the way, Randall Munroe, the artist behind XKCD, did a neat illustration of the IP space, which I recommend you check out. Anyway, so the RIRs together are loosely organized as the Number Resource Organization, or NRO, which helps coordinate Internet governance on this level. Now each of the RIRs have been assigned IP space by IANA, and can then further divide and assign those net blocks to the so-called local Internet registries to use or further allocate. Most of these LIRs are Internet service providers, or academic institutions, as well as large-scale enterprises, as shown here under ARIN. So to answer our earlier question as to how Stevens got its IP space, it was allocated to Stevens by ARIN from a net block assigned to it by IANA. Now ARIN is however a bit of a special case. Due to the US-centric management of the Internet in the early days, ARIN did receive a large number of historical allocations, which it then may further allocate to another RIR, such as in the example of the 157.92/16 net block shown here, which it delegates to LACNIC, which LACNIC may then further delegate in its entirety to, as shown here, the University of Buenos Aires in Argentina. So we see that IP space may actually have geographical properties, and if you've been working with these net blocks for long enough, you may even have memorized some and know that, hey, this traffic connecting to my system comes from Asia, for example. But that can be a bit misleading, since obviously IP addresses do not have a specific physical location inherently bound to it, but rather it's a question for the administrative ownership of the IP space, but that in turn can be used to seed the geolocation databases around the world. Anyway, the LIRs now further delegate the net blocks as they see fit, possibly dividing them using netmasks, as we discussed in a previous video. For example, we know that Stevens, having been assigned the 155.246/16 net block, has assigned the 155.246.89/24 net block to the CS department. And we can observe that Verizon, after having bought Yahoo a few years ago, became the new owner of the net block shown here, and specifically assigned several IP addresses to a specific service. We also note that the allocation from IANA at the top down to the end sites oftentimes follows some general rules. For IPv4 space, for example, IANA only handles /8 allocations, which it hands to the RIRs. The RIRs tend to divide the /8s into smaller networks and hand out, for example, /16s to the LIRs, which then can divide the network further, as we just noted. But okay, so now we know where IP addresses come from, but then why do we have IPv6 in addition to IPv4? Well, think about the allocations we just discussed. Our IPv4 space is 32 bits, because, well, that's what Vincerf thought would be a reasonable choice for a little experiment to see if this internet thing might take off or not. Turns out it did, and we've been stuck with this 32-bit space ever since. Even though 4.3 billion addresses sounds like a lot, it really isn't. For starters, we don't even get the full 2 to the 32 space for use on the internet. There are certain blocks that are reserved, as I mentioned earlier, the private IP space for example, as well as several other net blocks reserved for different purposes. Those together make up approximately 13% of the entire IPv4 space. But not only that, in the early days of the internet, allocations were made rather liberally, and so some of the early participants did get entire Class A networks assigned, over 16 million addresses assigned to AT&T, Apple, MIT, etc. The other problem is that organizations themselves have not been allocating space efficiently themselves, leading to fragmented subnets requiring additional allocations after the fact. And of course it's not helping that we're now putting light bulbs and refrigerators and toothbrushes on the internet, each requiring allocations too. So the 2 to the 32 addresses we started out with quickly began to be depleted. IANA exhausted its pool of unallocated /8 networks just about 10 years ago, and the RIRs then followed quickly, with APNIC in April 2011, RIPE in 2012, LACNIC in 2014, AARON in 2015, and AFRINIC in January of last year, meaning we are officially out of IP addresses in the IPv4 space. 4.3 billion addresses pretty much used up, a problem that we all knew for a long time was coming. Which is why IPv6 was introduced way back in '95, and why it's so disappointing to see that now, 10 years after IANA ran out of v4 addresses to allocate, we still have organizations and companies that do not support IPv6. But okay, so with IPv6, what are our default allocations? The RIRs generally get assigned a /12, which they then delegate to the LIRs in chunks down to a /32, which those then may delegate to endsites in chunks of /48s. And final end-user LANs, the addresses your Wi-Fi AP hands out to you for example, being for the most part a /64. Now think about that, most end-users will get a /64. That sounds incredibly wasteful. Sure, you can put all your refrigerators and TVs and light bulbs and toothbrushes on the /64, but you still have so many IPs left over that are basically wasted. Aren't we going to run out of IPv6 addresses in this way? To understand why this is not a problem, it's critical to understand just how large the IPv6 space really is. 2 to the 32 is 4.3 billion addresses, which we just realized really isn't all that much. Now you're all CS majors, so hopefully you understand better than the average person how exponentiation works. But let's illustrate just how many addresses we have available in the IPv6 space. So 2 to the 128 is a number that looks like this. 39 decimal digits, 340 undecillion, 282 decillion, 366 nonillion, a really large number. How large a number is that? Let's see how many IP addresses we can give every person on the planet. Okay, that's 4.41 times 10 to the 28 IP addresses per person. That's hard to fathom. How many atoms are there in a regular human being? Around 7 times 10 to the 27. So we could give 6 IP addresses to every atom of every single person on the planet. An internet of atoms. What's another thing that we know there are a lot of? I know. Stars. Oh, so not enough stars in the Milky Way to really make a dent here. How about the observable universe? Hey, we could give 340 trillion IP addresses to every star in the observable universe. What if every single star in the observable universe had a planet with people like us? Well, then we could give over 44,000 IP addresses to every person on an Earth orbiting every single star in the observable universe. That's how many IP addresses we have. And that's why assigning a /64 to every end user is not going to deplete the IPv6 address pool. Even though, by assigning a /64, or 18 quintillion addresses, we are giving every end user 4.3 billion IPv4 internets. I know, exponentiation is fun, isn't it? Anyway, I hope this little bit here gives you an idea of the size of the IPv6 address space. Play around with it some more. Wolfram Alpha is a pretty neat engine for this sort of thing. Alright, so let's pause here. We've seen how IP addresses are assigned. IANA allocates net blocks to the RIRs, which carve those up, and assign them to the LIRs, which then may further delegate or assign them. Now look around. Can you find out what IP blocks belong to which companies or organizations? How can you go about finding out what geographical region an IP block is allocated to? Next, to better understand what IPv4 exhaustion means in practice from an RIR's perspective, take a look at the information provided by, say, Afrinic, and see how many IP addresses they have left to assign. Also think about why it is that Afrinic is the last one to run out, and what that says about internet proliferation and traffic distribution around the globe. Think about what normally happens when a resource becomes scarce. Oftentimes a new market emerges. Can you find out where and how organizations could trade IP space they might not need any longer? All of these questions are intended to get you to think about the internet in real-world terms, meaning it is not an abstract thing, but has certain physical properties and implications. We'll go into some of the details of the physical structure of the internet in our next video. Until then, thanks for watching. Cheers!
Okay, so this time we have a segment 5, the physical internet. No? Internet censorship is the control or suppression of what can be accessed, no? Published or viewed on the internet enacted by regulators or on their own initiative. So internet censorship puts restriction on what information can be put on the internet or not. So individuals and organizations may engage in self-censorship for moral, religious, or business reasons to conform to societal norms, political views due to intimidation or out of fear or legal or other consequences. While some countries have moderate internet censorship, otherwise countries go so far as a limit to access of information such as news and suppress and silence discussion among citizens. So internet censorship also occurs in response to or in anticipation of events such as elections, no, protests and riots. No, an example is the increased censorship due to the events of Arab Spring. Let's say, for example, in other country, other types of censorship include the use of copyrights, defamation, harassment, and various obscene materials claiming as a way to deliberate suppress content. So support for and oppositions to internet censorship also varies, no, and that's what we have here. The physical internet, we have political, financial, application, presentation, session, transport, network link, and the physical for the physical internet. So we have here the submain cable map, no, as what we have here. Maybe you are familiar with, no? And the net interpreted censorship as damage and roots around it by John Gilmore, no? And the India leads the world in volume of internet shutdowns actually, no, and longest shutdown in a democracy, Kashmir, no, and economic cost after 6 months, that is 2.4 billion US dollar and nearly 500,000 jobs, no. So let's say for political, no, we have also considered based on the given sample, no. And I'll just want this will be actually the link, no, or the what they call this one, a link or a references, but I'll just want to show you a video presentations of a demonstrations and discussions of the physical internet, from political, no, to financial, application, presentation, session, transport, network link, and the physical layer internet. Okay.
Hello, and welcome back to CS615 System Administration. This is week 5, segment 5, and we're going to be talking about a few of the physical aspects of the internet. We saw in the last video that there's a logistical component to the internet. There's a non-profit governance body for at least some aspects of it, and we also noted that there's a geographical division, certain IP spaces allocated to specific geographical regions. Now this has necessarily political implications, and we'll get back to those a bit later, but having moved on from the abstract structure of IP packets to how addresses are allocated, let's now take a look at just how packets flow. By that we don't mean how do we route packets, although that's also interesting and relevant and something we'll discuss in the future, but we actually mean how does a packet get from A to B, physically. So we'll start down here at the bottom of the stack. Now if you have a point-to-point link, then it's rather obvious what path a packet takes. Packets go in here, packets come out there. You can follow the physical cable from one end to the other. Even if we're talking communications between your laptop and your Wi-Fi access point, it's still reasonably easy to understand the connection. Once the packet arrives at the access point, it then goes into the cable, and then from there it is delivered from your ISP to some switchboard in a machine room or data center somewhere, where, let's say, the packets enter the matrix. At this point, most people start to lose the overview of what's going on. Even CS majors may only have an abstract idea of what the internet looks like at this level, and claiming that it's a series of tubes is really not that terrible an analogy as people like to ridicule it to be. After all, we are hooking up cables here and there, and packets flow through them, taking turns, being redirected, and so on. But the internet is a global network. It's easy enough to imagine physical cables being run across the country between buildings, and you can of course correlate a lot of the data flow with population, which is why most of the action does happen just exactly where you see lights here on this image from NASA. But now let's think about where we find the largest spots of concentration here, and just how are we going to get our packets from here to there? But it turns out that it's not really a new problem. We've been trying to get communications between the continents for hundreds of years now. In fact, we've been doing that since the 1850s, when people first started stringing really long cables across the ocean floor to enable telegraph communications between America and Europe. And just like back then, we still do just that, which I find fascinating. That is, we're actually running these long cables from one country to the other by dropping them on the ocean floor, using these huge special-purpose ships that have thousands of kilometers of network cables rolled up in these huge coils, and which are buried on the ocean floor with special submarine cable plows. But they're not always buried. Sometimes they are just left on the ocean floor, but yeah, that's what we do. It's simultaneously high-tech, and yet still obviously simple. A really long cable. And this is one of those physical aspects of the internet that is useful to keep in mind, because there are a number of implications. On the one hand, you can't possibly get a faster network connection than, well, with a distance of roughly 5,800 kilometers between New York and Paris, and the speed of light being almost 300,000 kilometers per second, means that a round-trip packet cannot possibly be faster than 40 milliseconds. Though of course there's some overhead, and we haven't quite reached pure light speed between any 2 points. But anyway, so we've been stringing cables between countries, cables known as the submarine internet cables. They are operated by different companies, including communications providers, as well as some of the internet giants. This website here, submarinecablemap.com, allows you to zoom in and inspect all the various cables, which is really interesting. But think about what it means, running a cable on the ocean floor. There's all sorts of things that can go wrong with a network cable just sitting there, right? One thing that's pretty interesting here is that of course these cables carry electrical signals, and many animals have pretty acute electrical sensors. So it's really no surprise that they will every now and then get curious about what this long string on the ocean floor is all about. And there have been cables that were damaged by curious sharks, because when you're a shark and you sense something of interest, what are you going to do? You take a nibble to see just whether or not you should eat the thing. You know, might be tasty. But you know what else can happen when you have a cable sitting out there in the open? Well, think about where the cables are run. As we can see, these submarine cables are not only out in the open ocean, but oftentimes are closely hugging the coastlines, where there's a lot of industrial ships carrying cargo. And what do ships do when they are waiting outside a city's harbor? they throw their anchor down, which scrapes across the ocean floor to keep the boat from moving. And such an anchor may actually cut the internet cables by accident, which in turn may lead to significant internet outages. But let's take a closer look at some of these cables here. As you can tell, there's quite a lot of them. Let's pick this one here, Havfrue AEC2, which connects Denmark, Norway, and Ireland to the United States. An almost 8,000 kilometers long cable run by a consortium including Facebook and Google, able to carry 108 terabytes per second. The landing point in the US is right around the corner from Stevens, in the illustrious Wall Township, New Jersey, run by the New Jersey Fiber Exchange, or NJFX, where several cables land. The Confluence 1 cable running down the East Coast, for example, as well as the Seabrass 1 cable, which goes all the way down to Brazil, over 10,000 kilometers in length. Over here, on the other side of the US, we have cables crossing the Pacific Ocean, such as the Japan-US cable, which makes a pit stop in Hawaii. And over here, in Karachi, Pakistan, we see the Southeast Asia, Middle East, Western Europe cables, which run from Singapore to France, and which in a major global internet outage taking place in 2008 were accidentally cut, leading to several countries at least partially losing internet connectivity. So as you can tell, there's a significant risk of severe impact if these major communication lines are disrupted, whether by accident or by intent. Now, of course, you may have heard this quote by John Gilmore: "The net interprets censorship as damage and routes around it," which attempts to stress the benefits of the by and large distributed nature of the internet. But unfortunately, this is not entirely true. That is, if you are committed, in a position of significant power, and willing to accept the consequences, then you certainly can censor or disrupt the internet for a large portion of your citizens. And dictators and authoritarian governments have been increasingly making use of their powers here. As I'm sure you're aware, people in power are quite afraid of the common people's ability to communicate freely, and so the internet necessarily represents a great threat to them. Whenever there's a revolt, an uprising, or political upheaval, you can bet that the government in power will try their best to suppress the people's ability to communicate with one another. Just yesterday, there was an example of Myanmar cutting off its people from the internet amidst the public protests of the coup d'etat by the Myanmar military in February. What you see here is a graph of the average network connectivity in Myanmar. Since early February, the local ISPs had been ordered by the military to block Facebook amongst other sites, with increasing blocks since then. Now, this is not a rare occurrence. Every day, governments are willing to pull the plug and cut off their own people off the internet, such as Iran in 2019, when the Supreme National Security Council ordered a complete blackout during the ongoing protests there at the time, which was one of the biggest complete shutdowns for a large country like Iran. But it's not just authoritarian countries like these. India, the world's most populous democracy, is currently the sad leader in the number of internet shutdowns, where the government frequently orders parts of the internet to be turned off or restricted. India holds a sad record of having imposed the longest shutdown in history, when the Jammu and Kashmir regions were put into a preemptive lockdown, which, after 6 months, incurred a cost of over $2.4 billion and 500,000 jobs, illustrating that access to the internet at this point really is a basic human right that governments are unfortunately increasingly willing and still able to restrict at will. If you control the legal entities in charge of physically moving packets back and forth, you can restrict people's access. But such power does not merely extend to a binary on or off state of the internet. Rather, you are able to access all of the communications flowing through the physical devices that you control. And so if you have the legal power to force even a private enterprise to eavesdrop on all packets zipping by, then it's no surprise that governments, like that of the United States, also do this. What you see here is Room 641A, a secret network closet in AT&T's SBC Communications building in San Francisco. Or rather, it was secret, until an employee at AT&T noticed that for some reason there was this locked room that apparently all network traffic was mirrored in. The employee who noticed this was Mark Klein, who then became a whistleblower, alerting the public to the fact that the US government performed warrantless spying on not only global communications, as just about any large intelligence agency does, but also wiretapped and data mined US citizens' communications. And all of this is to once more iterate the point that no matter how much we may focus on bits and bytes and software and system administration, at the end of the day, we are still all operating on layer 9 up here. All the work we do is inherently political. Work on the internet enables or prohibits the free flow of information. Connectivity and routing and network protocol design all must take into account accidental or intentional abuse. And we must understand the impact and abilities of powerful actors, such as your own government, and, as Mark Klein showed, at times we must make difficult decisions with consideration of the political impact above that of your job security. Because even if we don't ourselves run the cables between different jurisdictions, the physical aspects of the internet remain an ever-present factor in our work. We'll pick up the ethical dilemmas we may encounter in our line of work in future videos. Then in our next segment we'll look a bit more at network ownership and how we can see the political structure of the physical internet. Until then, please make sure to check out the various links included in the slides, read up on the various internet outages, and perhaps research some of the other major disruptive events on the internet. I'm sure you'll find a lot of interesting information that perhaps so far you hadn't considered in much detail, and perhaps you begin to see the internet as a more tangible, physical thing. Thanks for watching. See you next time. Cheers.
Okay, so this will be the network of networks. No? The simplest way of explaining the internet is to call it the network of networks. So it's the connection of computer networks around the world into one entity. So to speak, it's not one big computer, but rather numerous network computers connected together. So as what we have here, no, the network is the computer itself. No? And the network is the network, the computer is the computer, as what later we'll be able to discuss in the video presentation. So there is no cloud, only other people's computer. Okay? This will be an example, of course, of a networks, no? Because in the networking we have different type of networking topologies, no? As what we discussed in a data communications, no? Specifically the ring topology, no, the MASH, no, topology, and others. No, this will be a sample of a broadcast domain. No, autonomous system example. And as what I have here, this will be the internet domain name in network number directory service. No, for this. Later on, there is a demonstration on how we'll be able to understand these codes, no? And from autonomous system, we have different IP addresses, no, as stated here, no? And later on, we have a demonstrations on how we'll be able to deal with this code, and of course, peering, no? Peering, of course, when it comes to let's say, for example, for the yahoo.com, no, and some IP address at the same time. So we have here also a demonstrations later of the use of peering, no, in a Linux operating system. So we have the daily stats, no, daily traffic statistics of all co-locations combined, no, from daily, no, up to monthly stats and yearly stats, no, for the network of networks. So this will be actually the summary of the video discussions later. Now we could able to identify AS number of the other organizations and companies and find out where they peer, research and review some publicly known cases of the peering between ISP and how this could lead to degraded network performance for the respective what do you call this one, customers. Now review the list of largest internet exchange points and comparing their throughout the facilities. Try to largest in of course review the list of largest internet exchange points and compare their throughout the facilities. I'll just want to give additional input with pairing, no. So peering is a process by which two internet networks connect and exchange traffic. It allows them to directly hand off traffic between each other's customers without having to pay a third party to carry that traffic across the internet of them. So network peering is when one internet network connects to another, directly enabling a faster throughput in exchange of information. No additional charges are incurred and no third-party network is required. No, the typical connection to the internet is called transit. No, peering when two or more autonomous networks interconnected directly with each other to exchange traffic, and this is often done without charging for the interconnection or the traffic. Transit when one autonomous network agrees to carry the traffic that flows between another autonomous network and all other networks. So I just want to show you a video presentation for you to understand better the discussions of the network of network.
Hello, welcome back to CS615 System Administration. This is week 5, segment 6, and after we discovered in our last video that the internet has a physical component with real-world impact, we'll now look at exactly how the internet is comprised of independent networks. We've already seen that we connect to the internet across the globe by using, for example, submarine communications cables, which physically connect one continent to another. And we intuitively understand that obviously there are different legal entities controlling the endpoints of these cables, and thus the connectivity that is made possible by them. And so this is one direct implication of the nature of the internet, of it being not a single network, but a network of networks. And this network of networks has really taken off since its humble beginnings back in the 1960s and 70s, hasn't it? As early as 1984, did John Gage from Sun Microsystems coin the phrase, "the network is the computer," meaning that all the computers are merely connected interfaces to the larger network. You see, the idea of putting all your compute resources onto the network is not all that new. But admittedly, this led to some confusion, so it's useful to clear things up. The network is indeed the network, and the computer remains the computer. But now about that network. It's not really one network. And even though we all think of computing resources that are reachable via the network as being in magical cloud land, of course system administrators know all too well that there is no cloud, only other people's computers. After all, at some point, somebody, somewhere, has to maintain these resources. But okay, let's focus more on the network, or rather, the networks that make up this network. Networks have a tendency to grow. If we connect two endpoints, it's trivial. If we connect multiple devices, we need a network layer. As we've already discussed, if the devices are within the same broadcast domain, such as being connected via a switch, then we have a layer 2 network. And we can connect multiple such layer 2 networks with one another using a layer 3 device, a router. In this way, we've also already discussed the need to subnet our IP blocks, as you will recall. But so of course we will eventually want to connect multiple such networks. And when we do that, we begin to talk about autonomous systems, networks that are grouped together. The various networks within such an autonomous system may be made up of independent networks using separate IP space that has been allocated to the controlling entity down from IANA to the RIR and the LIR, as we discussed in an earlier video. And so as we connect these autonomous systems, we're building the internet. What you see here is a visualization of the routing path of the internet circa 1997, color-coded by which RIR assigned the space and grouped via connection paths. The central stars in this graph represent the systems that are connected to more other networks. This network looks a bit different now in 2021, with obviously more networks and more connections between the networks and more geographical regions, but still representing the routing paths as before. And these routing paths are based primarily on knowledge about exactly these autonomous systems, since the Border Gateway Protocol, or BGP, shares its routes, that is, the reachability of the different networks via which AS number it can talk to. But where do we get our AS numbers from? Who would better be in a position to assign AS numbers than the same entity that also allocates IP space? So yes, we once again go back to IANA, which allocates AS number blocks to the RIRs, which then allocate the specific AS number similar to how IP blocks are managed. Okay, so how do we find out what our AS number is? One way to look at the information about a given network block allocation is via the whois command, which queries the various network information centers via the whois protocol. As you can see here, the query usually starts at IANA and then may query the relevant RIRs for the information, and in this way the protocol is similar to the DNS protocol, which we'll discuss in some detail in a future video. So if we want to find out about our Stevens net block, then we pass in our web server IP address. And we can then see that IANA tells us that it had allocated the 155/8 block to Aaron, which then tells us that it allocated the 155/246 block to Stevens back in 1991. Aaron then also provides us with a URL that gives additional information about this net block. So let's see what they show us there. Hey, look at that, it's JSON. Neat. Looks like there's a fair bit of information about the net block and its owner here. Let's see if we can extract the AS number from this. There we go, Stevens' AS number is 16889. Now, if we look at the information from Aaron in more detail, we find that Stevens has been allocated multiple IP blocks, which we can then extract here too. Did I mention that I like JSON and JQ? Really useful. Anyway, so we see that Stevens has multiple net blocks, not just the 155/246/16 net block we see so often. In fact, it looks like Stevens also has an IPv6 net block allocated. It's just unfortunate that it doesn't seem to be used much. But alright, so now we can start to visualize how our network connects to others. Let's say that at the bottom network here represents Stevens, i.e. AS 16889. With its net blocks used in whatever way Stevens deems fit. But now, what is the AS number of the network that Stevens connects to? For that, let's just find out what the path is that our packets take when we talk to some web server on the internet. We'll be looking in much more detail into how the traceroute utility works in one of our next videos, but I trust you're familiar with it. When we trace our packets to, say, the Yahoo website, then we get back output that shows us the different hops along the way. Here we see that we're jumping from where we started to another address in 155/246/16, then an RFC 1918 address, that is a private network address, then some other 155/246/16 addresses, before we then leave the Stevens network and eventually find our way to the Yahoo networks. So now let's take a look at the first non-Stevens address here, 130.156.251.105. Okay, so this address is in a net block that's assigned to the New Jersey Higher Education Network. And we get the AS number. We'll use a different whois server here that's set up to provide just that information. There, that's pretty convenient, huh? Okay, so now we've identified the AS number of the next network, AS 21976 in this case, of NJ Edge. And we could do this manually for each hop along the way, but fortunately the traceroute utility has an option to do this for us. So we have Stevens AS 16889, then NJ Edge AS 21976, then AS 4637, and AS 10310, which appears to be Yahoo's AS number, but there's also AS 26101, showing that of course an organization can have multiple AS numbers. So with that information, our image of how the packets go through the different networks can now be filled in. Stevens AS16889 is connected to NJ-EDGE AS21976, which connects to AS4637 and from there to Yahoo's AS10310 and AS26101. So we see that the connections between the networks are made in specific locations, it seems. This process of connecting the different networks is called peering, and it takes place in the form of an actual physical connection between the systems of these entities, allowing them to exchange routing information via BGP. These connections are made at so-called peering points, or Internet Exchange Points, or IXPs, in strategically located data warehouses around the globe. And one of the great things about this, like so much on the internet, is that it's primarily public information. That is, we can look up who is peering with whom in what location via, for example, the PeeringDB website. So if we take the NJ-EDGE AS number 21976 and plug it in here, then we see a fair bit of information about this organization, including which IXPs it is peering at. One of them is the New York International Internet Exchange Point, or NYIIX, which we also see reflected over here in the DNS name of the next hop in AS4637, which belongs to Telstra. Which then connects to AS10310, which is one of Yahoo's AS numbers. And the entry here shows all the IXPs Yahoo peers at, which turns out to be quite a few, all over the globe. Now, the packets hopped around AS10310 for a bit, before going into AS26101. But we don't find that AS in the PeeringDB. And neither do we find Stevens AS16889 in the PeeringDB, because both of those networks do not peer with any other networks. That is, not every network directly peers with others at a public IXP. In addition to the public peering locations, there are also, of course, private connections that are made, such as between Stevens and NJ-EDGE, which provides the network connectivity to the larger internet here. The larger networks, like Telstra's AS4637, then connect many more other networks, and thus become a central point in the network visualization we saw at the beginning of this video. Now, as you can imagine, these peering points, the internet exchanges where these connections are made between the large carriers, need to have some big pipes. And as that is a large selling point, you can often find some interesting stats on their websites. The Amsterdam Internet Exchange is one of the largest IXPs in the world, and it shows a daily throughput of 9.4 terabit per second. The daily stats show nicely how traffic drops down a bit at night, ramps up during the day, peaks after dinner, and then drops off again. Monthly and yearly stats then show an increase in overall throughput over time. The German DECIX, another one of the world's largest IXPs, also has some stats with similar patterns. As does the Moscow Exchange, although here the throughput is a bit lower than in Amsterdam or Frankfurt. With even lower rates for IPv6, it appears. Hello, welcome purely identical in style. This is no surprise, as they are generated using the Toronto Exchange stats. Monthly and yearly stats then show an increase in overall throughput over time. The German DECIX, another one of the world's largest IXPs, also has some stats with similar patterns. As does the Moscow exchange, although here the throughput is a bit lower than in Amsterdam or Frankfurt. With even lower rates for IPv6, it appears. The NY-IIX stats look like this. The Toronto Exchange stats like this. And the NetNod exchange in Sweden like this. As I'm sure you've noticed, the graphs all look similar, not only in the patterns they show, but also eerily identical in style. This is no surprise, as they are generated using one of the standard open source network traffic graphing tools around, MRTG. Even JPNAP seems to be using MRTG, and if you get involved with any network architecture and administration, you're quite likely to become very familiar with graphs that all look like this. Alright, I think we can break here and conclude our journey through this network of networks. To ensure you internalize the lessons we illustrated here, I recommend that you try to identify AS numbers of other organizations and companies and find out where they appear using the tools we've shown in this video. Try to find out what happens when two organizations develop a dispute and one wants to depeer, to remove the connection with the other. There have been several cases where two competing companies used this or the threat of depeering as a means to harm their competitors. On Wikipedia, you can find a list of the largest internet exchange points, and you can browse their websites to find some stats like we showed a second ago. But there are also some locations that are less open. The network access point of the Americas, for example, is housed by Equinix, a huge colocation provider. Try to find out more about these exchanges. Finally, if all of this interests you enough that you want to be part of the community of network operators that literally and physically built the internet, you can join the North American Network Operators Group, or NANOG. The public mailing list is a really interesting place to hang out and learn about the structure of the internet and the various aspects most people higher up the stack never think about. Okay, and with that, we're concluding our first week of networking, but as I promised, we're not done yet with this topic. In our next couple of videos, we'll again go down the packet level to trace traffic of different applications and protocols, but we also will need to take a look at just how our host knows how and where to send packets. You'll be getting intimately familiar with TCP-dump and the various trace tools. Hope you're looking forward to it. Until then.
Okay, so that is for now, and next time, or next meeting, we're going to have a discussions of a continuation of networking, that is networking number 2. So based on the continuation actually of the networking one. So thank you and enjoy the rest of the day.